All right, welcome to the second question of this essay. And so today we're going to talk a little bit about the resting membrane potential. And to do that, I'm going to start out by drawing a cell here. And then we're going to draw a couple different channels. And also we're going to draw a sodium-potassium pump. So here we have 3 sodiums leaving, 2 potassiums coming in by source of energy, which is ATP. And then here we have a sodium voltage gated channel. And here we have a potassium leak channel. And so to back up a little bit, the resting membrane potential of the cell is negative 70 millivolts. And so we're going to talk a little bit about why that is. And so one of the reasons why it's negative is because we have negatively charged proteins that kind of are all along the inside of the membrane, which cause the inside of the cell to be more negative. But here we also have this sodium-potassium pump, which is pumping 3 sodiums out and 2 potassiums in. So we get a higher concentration of potassium in the cell and a higher concentration of sodium out of the cell. And it starts causing this concentration gradient. And when the cell is at rest, the sodium voltage gated channel is closed, so no sodium is getting in and out of the cell. And this is also due to the permeability of the membrane. But with the potassium leak channel, we have this gradient that is pulling potassiums out. And so potassiums are leaving behind these negative charges, which is causing it to be a little bit, it's causing that negative voltage inside the cell. And a lot of these things deal with help with like the magnitude of the membrane as well, the RMP. But another big thing with the magnitude is if you change the extracellular concentration for specifically and particularly potassium, you get a change in the magnitude. And so, for example, let's say we have hypokalemia. Hypo means less and emia means blood. So we're going to have less potassium on the outside of the cell. This is going to cause this concentration to be stronger, pushing out more potassium, leaving behind more negatives. And so with hypokalemia, we have a more negative RMP because of having that less potassium on the outside of the cell. And another concept that is important to understand is driving force. And so driving force can be calculated by the RMP minus E. And E here is the Nernst equation. And so the Nernst equation is it's an equation that you use, but certain assumptions have to be met, which isn't the case in biological systems because it's assuming that everything is 100% permeable, which isn't the case in those biological systems. And so that's why the driving force is important, but you need to be able to calculate the Nernst value. And so to do that, it's this equation right here, where Z is the valence charge. Then you'll take the log of the concentration of the ion inside the cell over the concentration of the ion outside of the cell. And from that, we can calculate our Nernst equation, and then we can take the value of our RMP, subtract that from the Nernst equation value, and we'll get our driving force. And depending on the value of the driving force will tell us the direction that the certain ion is going to go. And so to show you what the values do, we'll make a little graph here. So we have the driving force, and we'll have a positive and negative value. And depending on if it's a cation or anion, it's going to either go in or out of the cell more easily. And so we'll start with the cation. If the driving force of a cation is positive, it's going to leave the cell. And if the driving force of a cation is negative, it's going to go inside the cell. And it's the opposite for an anion. If it's positive, it's going to go inside the cell. And if the driving force is going to be negative, it's going to be outside the cell. Okay, so now we're going to talk a little bit about action potentials. And to begin, I will just draw what an action potential graph looks like. So we have time, and then we have our millivolts. And here's negative 70, minus 50, plus 30. And then after I draw this action potential, we'll talk about each part of the graph and then what is happening on the membrane to make this happen. I know this graph isn't perfect, but just pretend that this is a normal action potential. And so to start, we just need to understand a couple terms. And so if we're to draw this right here would be a graded potential. So a graded potential is when a stimulus is still happening inside, but it's not strong enough to hit this negative 50, which is our threshold. And then once we hit this negative 50, this is when the action potential takes place, and that's when we get the action potential right there. And a couple other terms to know is this is what we call depolarization. And then this is repolarization. And then hyperpolarization. And then when it's at negative 70, which is its RMP, we could just call that polarization. And then a couple other terms to know is during the depolarization and repolarization phase, so this phase kind of right in here, we have what you call your absolute refractory period. And then right along in here, in like the hyperpolarization phase, we have the relative, we'll just use purple again, the relative refractory period. And so the absolute refractory period is when no matter the stimulus, another action potential cannot occur. And the relative refractory period is once it begin, like once you can start having action potentials start up again and be propagated. And so now we will talk about what is happening at each phase during this action potential. And so right here at the beginning, it's the resting membrane potential. Like we just talked about, like not a whole lot is happening. Like there's always going to be potassium leak channels open, which is causing that negative 70 millivolts, but nothing else is happening. And once the stimulus is strong enough and hits this negative 50 right here at threshold, that is when we're going to have the sodium voltage gated channel activate. And all this sodium is going to flow into the cell, and that's why we get this depolarization phase right here. And then about at this point, those sodium voltage gated channels begin to close and potassium voltage gated channels begin to open. And so the potassium is going to want to flow into the cell. And then that's when we get this phase right here. And then once we get to like right here, the sodium voltage gated channel is going to be completely closed, and the potassium voltage gated channels are going to be open, and it's going to flow in super quick. And then once we hit the threshold going back down, we're going to begin closing those voltage gated potassium channels. And then right in here, we're going to have all of the potassium leak channels open as well. And then there's still going to be some voltage gated potassium channels. And then once we get to this polarization phase right here, once we get back to the RMP, there's only going to be the potassium leak channels open like it was here right at the beginning. And so that is a little bit about action potentials. And so now we'll talk a little bit about how these action potentials move along a neuron, because a neuron is very long, and so one of these won't allow for it to do everything that it needs to. And to understand that, we need to first understand what a length constant is. And I will begin by drawing a neuron here. So we have this neuron, and the length constant can be calculated by taking the square root of the Rm, which is the membrane resistance, over the Ri, which is the resistance inside the cell. And basically what this is trying to say is, what is the sphere of influence? And so we'll put right in here, we'll put a voltage gated sodium channel. And so this sodium is going to want to flow into this cell, and it's going to have all these positive charges. But these positive charges aren't going to just flow down naturally and cause all those negatives to become positives, because we still have all these negative charges inside this cell. Sorry, I'm just creating some channels in here. And so we have all these positive charges. And so what the length constant is saying is how strong is the sphere of influence? How far are those positives going to travel? Because we have all these proteins that are negatively charged and all these things are causing it to not want to travel along the membrane. And that is when we get into capacitance. So the equation for capacitance is Q over the voltage, where Q is our charge separation, and our volts is going to be in millivolts. And so right here, we still are going to have some voltage gated sodium channels, but we're also going to have potassium leak channels, and these bumps right here, these is myelin. And so once it goes, all these positive charges are going to want to stay along this membrane, and so only a couple are going to get along this myelin. And so what capacitance is trying to say is that when we have all these positive charges, we're going to have a higher capacitance, where here there's going to be lower capacitance. And so what that is saying is once the sphere of influence gets to here, it's going to travel further. Going to travel further because there's those less negative charges, and it's going to increase the speed of that sphere of influence, and so more action potentials are going to be able to occur. And that wraps up essay number 2.